So we left off on the D3 electron configuration. At first, we tried to pair the electrons as much as possible. That's one possible electron configuration. That was spin 1/2 or doublet. Here, it's sort of like a high spin equivalent, right? This would be high spin. We don't call it high spin or low spin because, as it turns out, for certain electron configurations, as you'll see in a second, you can have more than two choices. You can have a low, intermediate, and a high spin. So the high spin business, mostly people just refer to when they're talking about octahedral or tetrahedral, but you could call this high spin, D3. It is higher spin than the doublet was. And again, what would we call this? We could call this spin 3/2. And we know the spin multiplicity is given by 2s plus 1. So we would call this what? This would be 2 times 3/2 plus 1, that equals 4. So we call this a quartet. Okay, so this is a quartet. And so to maintain a quartet, that means we have to have one electron in this higher energy state for TPP, one electron in square pyramidal in this higher energy state. We go ahead and we add up all these together, right? So we have 2 in the 7/2 epi with 7/2 epi energy. So that's going to be a total of 7 epi there, and then we have 3/2 extra epi. So 7/2, that's 14/2 total on the bottom, plus 3/2, that's 17/2, and then plus the 9/2 epi sigma. So just summing it up, here you have 1 in the 4 epi and 2 in the 3 epi. That's a total of 3 plus 3 plus 4, 10 epi. And so from this one, we know, right, epi is way less, whether or not it's positive or negative, it's way less than E sigma, which is always much bigger. And so that's going to tell you this is definitely going to be square pyramidal. It doesn't matter what type of ligand you have, because in TBP, you had to put it in this higher energy state that was worth 9/8 E sigma. That's always going to be higher energy. And so here's an example of a D3 complex that is a quartet. And so there's various ways to figure out if you have a quartet. One of the most common is EPR spectroscopy, electron paramagnetic resonance spectroscopy, which is basically, you can think about it as it's the equivalent of doing NMR except for electron spins, right? NMR is for nuclear spins. But anyway, we're not going to have a time to go over EPR in this course, but just know that, that's one way you could figure out what the spin state is. So this quartet, this angular overlap method correctly predicts that this quartet D3 is going to be square pyramidal. All right, so now we can move on to D4. D4 is going to be a singlet, 2s plus 1, s equals 0. That's going to be a singlet. And this is going to be total energetics of 14 epi versus 12 epi. Again, this is pretty close. 2 epi is not a big energy difference. And so if this is similar to where we were with some of the previous examples, where if we have a strong pi donor ligand, we might slightly favor square pyramidal. And that's because in that case, epi would be very positive, okay? But most of the time, sterics are going to win here. So you're going to have the trigonal bipyramidal structure. We can go look at another spin state. So this would be a triplet, 2s plus 1, D4 configuration. And here it's pretty clear that square pyramidal is going to win because, again, we have one electron in this 9/8 E sigma term. That's very large. Now we can go into a pentet stage. Okay, so this is all 4 electrons are unpaired. S equals 2, so we call this a pentet. And that pops up a electron into this dz squared, which has an energy of 2e sigma. And so now look, our epi's actually happen to be the same energies here, both at 10 epi. And so we're at 2e sigma versus 9/4 e sigma. And this is fairly close, right? We're talking about basically So 9/4 E sigma is what, 2.25 E sigma. So these are very close. These are only 0.25 E sigma away. And so it's really going to depend upon the ligand size here. It's not going to depend at all upon the pi donor or pi accepting ability of the ligand, because look, those are the same, right? It's 10 E pi for both geometries, so that's not going to make a difference. But we know that bigger ligands would favor TBP just because sterics would give rise to, steric clashes would give rise to less effective overlap. And so then you're always going to favor the sort of VSEPR structure. So you can see that here's two examples here, where this is manganese in the +3 oxidation state. That's a D4 metal center. And with small chlorine ligands, it's square pyramidal. But when you put these big phosphines on there, same oxidation state, 3+, it ends up being trigonal bipyramidal. Here's also an example, right? You had a high spin case, a pentet, intermediate spin case, triplet, and the low spin case, the singlet. So it's kind of why we stop using the terms low and high spin. All right, so let's go on to D5. D5, we can do spin 1/2. This is a doublet with one unpaired electron. And you can see TBP clearly is higher in energy, so square pyramidal is going to win. You have this 9/8 E sigma factor that's just going to dominate the energetics here. We can go on to the next spin state, S equals 3/2, D5. Here, things are pretty close again. We have 2 E sigma, and again, we have that 9/4 E sigma, so that's 2.25 E sigma. Here we have 13 E pi, and here we have, what's that, 13.5 E pi. So that's very, very similar there. So it's going to depend upon the ligands a lot, with a preference for, bulkier ligands favoring TBP and smaller ligands favoring SP. Smaller ligands that were really pi donating would really favor square pyramidal, right? Because you have both this slight E pi factor happening and this slight E sigma factor working in square pyramidal's favor. What about D5 with a spin of 5/2? That's kind of interesting. So now you're in a sextet, right? 2s plus 1, 2 times 5/2 is 5, plus 1 is 6, so we call it a sextet. These are actually equal. And so if they're equal, sterics wins. So no matter the ligand, steric is going to win because you're always going to have some non-ideal overlap there that will help the TBP case. All right, and indeed, this is what you see. Something like this iron chloride complex is trigonal bipyramidal. D6 with singlet state, actually only square pyramidal is possible in this state. And why is that? You can try to pair up the electrons here. So how would you do this? Well, you want to pair them up as much as possible because you're making a singlet. So you go, okay, boom, boom, pair. And then you have one here. And then if you try to pair it to make a singlet, you'd be violating Hund's rule, right? Because these are degenerate. So there's no reason. This is always going to be an excited state compared to a triplet, right, where you have that. So that's why you can't have a singlet be D6 trigonal bipyramidal. Kind of interesting there. So you're going to be square pyramidal for sure. And there are some cobalt porphyrin or macrocycle things, okay? Macrocycles are complexing agents that, that are square pyramidal. You can have other spin states in both though, so consider this triplet, D6, and these are pretty interesting. Again, it's pretty close call here. 2.25 E sigma versus 2 E sigma. So similar to some other cases we saw before, going to depend on the ligands. Lastly, we have this pentet state, D6, and these are very close, right? The 5 E sigmas cancel are ties there, but we have a 13/2 E pi and 13 E pi. So probably, 0.5 e pi difference isn't a lot. So probably you're going to figure you're going to prefer the sterically preferable geometry of trigonal bipyramidal, unless you have a very, very strong pi donating ligand where that 0.5 e pi would make a difference. Then you might get rise to square pyramidal. On to D7. D7, we got to double it here. These are looking fairly different. We have 2 e sigma for square pyramidal, and we have 3 3/4, 3 3/8 e sigma on TBP. So, that's a difference of more than 1 e sigma, definitely going to be square pyramidal. If we go to a different spin state, spin equals 3/2, very similar here. Just 1 e pi difference, the e sigma terms are the same. And so this is the same pattern we've seen before, where you're going to probably be TBP, but if you have a strongly donating ligand, you might be SP. And so here's one example, kind of normal ligands, nothing strongly pi donating, it's TBP. Singlet state for D8, you have, let's see, 9/2 e sigma and 4 e sigma on the right side for square pyramidal, 20 e pi. Here it's a kind of a judgment call a bit, not a super obvious one. You're only 0.5 e sigma away, so if you have a really bulky ligand, you're probably going to be TBP, but otherwise you would be the lower energy state of square pyramidal. We can do the triplet state here. Now you're at 5 e sigma there versus 49/8 e sigma right there. And so that is, greater than 6, that's 6 1/8 e sigma. So you're greater than 1 e sigma difference, 1 e sigma higher on TBP. So it's not going to be TBP, it's going to be square pyramidal kind of no matter what the ligands are. Moving on to D9. D9 are looking pretty similar, just a little bit different in terms of e sigma. E pi's are the same. Not going to care about the pi donating ability or pi accepting ability of ligands. Going to just care about ligand size, bigger ligand size, favoring TBP. And that's borne out by these two examples. Copper halide complex with pretty big ligands, bromide, whereas this ammonia, those are pretty small atoms, so everything can kind of fit in there. Even though you have more atoms, protons really don't take up that much space. Lastly, D10. D10, everything's filled. And when everything's filled, the energies are the same. So that's back to the VSEPR structure, TBP. And this is in chloride complex. That's D10. That's a zinc in its second oxidation state. Zinc is in group 12. And so that gets you a D10 metal. So that's it, guys. This was one example showing you, really we just went over one example showing you how powerful the angular overlap method can be. But, this is very simple to use, these ideas. And so all the concepts about whether or not, the steric geometry is going to be preferred, whether or not a pi accepting ligand is going to be helpful in stabilizing one geometry or a pi donating ligand. Hopefully all that logic is clear. If not, let's go over it together. But you'll be practicing this in the homework and on the exam. Basically I'm going to ask you for another set of 2 different geometries to make these Walsh type diagrams and make predictions for different electron configurations as to what structure is more stable. Okay, so that's the end of chapter 7. So I'll see you next time at chapter 8.